Swayam Prabha. Digital India. Educated India.
Hello students. So in continuation to the discussion of different tools and techniques, today we'll be introducing the concept of Geosm-Natec. But before that, let us also have some good discussion on the summary of previous modules so that we can recap what we have studied in previous weeks. So today first I will be discussing the module 6 in continuation, the ecosystem services. In this, the first lecture of this particular module, lecture 26, talked about the key concept of ecosystem services, which are the benefits humans derive from the natural ecosystem. The cascade model, which links ecological structures and processes to functions and human well-being. We discussed Dr. Dasgupta's inclusive wealth framework, which integrates natural capital with the produced and the human capital. The field has evolved from functions of nature to IPBES as nature's contribution to people. And the keywords in this particular lecture was natural capital, cascade model, nature's contribution to the people. In the following lecture, we have discussed types of ecosystem services. Ecosystem services are classified into provisioning, regulating, cultural, and supporting services. Provisioning services supply material goods like the food, freshwater, raw materials, and medicine. Regulating services maintain balance via climate control, water purification, and pest control. Cultural services provide non-material benefits like recreation, spiritual value, and aesthetic enjoyment. So the keywords for this lecture, if we have to select, are the provisioning, regulating, cultural, supporting services. Millennium Ecosystem Assessment Group has already actually done all these. Evaluation of ecosystem services, we discussed it in two parts. The first part was on biophysical. Evaluation connects biophysical supply with socio-economic demand for decision making. The invest models, the spatial distribution and economic value of ecosystem services for scenario analysis. That is the contribution from the invest. We also discussed other models like ARIS, which uses artificial intelligence to map service flows, quantify beneficiaries, and assess uncertainty in the system. Biophysical assessment is the foundational step before performing economic or sociocultural valuation. So, we discussed in this particular lecture invest, ARIS, biophysical valuation, supply and demand, and spatial mapping. In the next lecture, where we continued this evaluation discussion, we discussed the total economic value, TEV, which aggregates direct, indirect, option, and non-use values, economic valuation methods, which include market price, travel cost, hedonic pricing, and avoided cost. Non-use values like existence and bequest, which reflect ethical, altruistic, and future-oriented benefits, that also we discussed. Sociocultural tools like solves, which map perceived non-monetary values and social preferences, were part of our lecture. So the keywords TEV, the total economic value, willingness to pay, solves, and hedonic prices, as well as the existence value, were part of this lecture 29. And the last lecture of this particular module was urban ecosystem services. So, urban ecosystem services are distinct due to high demand, fragmentation, and hybrid engineered systems. At the neighborhood scale, one can focus on street trees for microclimate regulation and shade. At the city scale, one need to manage the stormwater and waste through urban wetlands and blue-green networks. So that is the urban ecosystem demand at the city scale. At the regional scale, we utilize the urban ecosystem services like peri-urban forest for carbon storage and air purification, etc. So the keywords in this particular lecture were urban-rural gradient, microclimate regulation, stormwater retention, green-blue networks. Followed by that, in the next week, we discuss this module 7, development and ecosystem. And in the first lecture, we discussed effects of urban development on ecosystems. The key concept discussed were urban development drives, land use, land cover change, and habitat fragmentation. Biotic homogenization, which replaces native specialists with global urban adapted generalists, synanthropes. The urban heat island effect results from low albedo thermal mass and reduced evapotranspiration. Impervious surfaces disrupt hydrology by blocking infiltration, increasing runoff, and heightening flood risk. The keywords we discussed are the urban heat island, LULCC, and biotic homogenization and the hydrological disruption. Next lecture was on urban ecology, which evolved from studying organisms in cities to the ecology of cities as systems. Cities are complex adaptive systems defined by nonlinear feedback and emergent properties. The ecology with cities framework emphasizes co-production, stewardship, and participatory governance. Urbanization creates novel ecosystems where synanthropic species thrive in human-altered environments. The keywords in this lecture was the social ecological system, the complex adaptive systems, ecology in, ecology of, ecology for, and ecology with cities, and the novel ecosystems. Next lecture was on social aspects intertwined with the urban ecosystem. The key concept was social, ecological, technological system framework, which integrates social, ecological, and technological dimension of cities. Environmental justice we discussed, which addresses the unequal distribution of green benefits and pollution burdens. Green gentrification, first time probably we introduced in our discussion, which occurs when ecological improvements displace vulnerable low-income residents. Stewardships and place attachments foster deep human nature connections and civic engagements. Keywords are ACTS, environmental justice, green gentrification, co-production, place attachment. And in the next lecture, urban landscape ecology as a planning strategy, we discuss the patch corridor matrix as the key concept. This model, PCM model, analyzes cities as mosaics of habitat and built structures. Connectivity theory, which uses corridors to facilitate ecological flows and species movement across the matrix. Landscape metrics like patch density quantify fragmentation to guide restoration and planning. Strategies include multifunctional design and green networks like Barcelona's superblock. The keywords used in this particular lecture was PCM, connectivity, fragmentation, superblocks, least cost path. And the final lecture of this module was role of urban governance for ecosystem protection. Governance shifts from state control to polycentric collaboration with non-state actors. So it's a very strong understanding without which we cannot really look for improvement. Institutional fragmentation or silos often hinders effective cross-boundary ecosystem management. Tools like green bonds and transfer of development rights, TDR, that finance and incentivize conservation. The 74th Constitutional Amendment mandates urban local bodies to protect local ecology. Polycentric governance, 74th Constitutional Amendment, green bonds, TDR, silo problem were the key words of this particular lecture. So this is module 6 and module 7, which we have which we brought back for our recap. And now for today, we will be discussing very new framework, that is Geosm-Natec toolwork, and we will discuss about its architecture and methodology and Geosm-Natec framework potential solutions. That also we'll discuss. So this Geosm-Natec is a framework which the full form of it is the Geospatial Mapping of Natural Ecosystem framework, and it is for smart research, smarter decisions in urban risk resilience. And this framework helps in urban risk resilience using remote sensing and GIS platform for nature-based risk mitigation. This particular framework is developed in the climatology lab of the Department of Architecture Planning of IIT Roorkee. The Geosm-Natec approach uses the geospatial tools to diagnose the health of these ecological systems. It views the city not just as infrastructure but as a living system. So we can see the goal of this Geosm-Natec framework's application is to move from parasitic cities to regenerative cities. What it is, this framework? A multiscalar framework integrating Earth observation data, GIS, and multi-criteria decision-making system. The core components of Geosm-Natec framework is data acquisition, processing, and modeling and decision support. Data acquisition, satellite sensors data, processing spectral indices and the thermal retrieval, and modeling based on entropy and suitability analysis. And it helps in decisions for zoning for nature-based solutions. So we can identify the problem side, those hotspots, as well as we can identify the areas where the solutions can be implemented. So Geosm-Natec framework is having this advantage: problem identification and the solution, holistic cycle. So the geospatial mapping of natural ecosystem framework is technology-based spatial decision support system. It has application of GIS analysis and remote sensing techniques. New urban risks and their changing trends in the past decades can be identified using this framework. Hotspots identification considering multi-hazards can be done. It assists in identifying zones of intervention. It identifies urban blue and green areas suitable for reducing disaster risk with nature-based solutions. As part of a planning process for a project that aims to assess risk zones and integrate nature-based solution options into its planning, Geosm-Natec framework is the best support. Architecture and methodology of this Geosm-Natec, you can go through this conceptual methodology. The first phase is gathering and compiling the information for the analysis. Phase 2 is preparation of geospatial layers based on that analysis, and phase 3 is the outcomes. So the flowchart talks about gathering the data, and which is very important because the data, both the quantity and quality, will make sure that your analysis and your insights development is the correct one. So the study area selection, your interest area, then information and geospatial data layers for different urban risks. Segregate the data layer based on hazard, vulnerability, and exposure. So you create separate hazard layers, vulnerability layers, and exposure layers. Once that is created on the GIS platform, you start mapping the geospatial layers on this GIS platform, and grid-wise layer data extraction you can do now, and you do the analysis of this extracted layers data based on predetermined conditional approach. Identification of risk zone categories and hotspots validation is the very first task you can do in the next phase. And identification and categorization of blue-green infrastructure potential zone, and then the intervention zone identification. And here comes the role of the participation from the community, because we cannot decide anything without having understanding that how those sites are going to really be managed, maintained and operated later on. Phase 1 is the gathering the data. So gathering and compiling the information for the analysis. Demarcation of the study area is the first step of phase 1. Information and identification of geospatial data layers of the urban risk, that is the next stage, and followed by the third stage, that is segregation of geospatial layers under the three heads of risk functions, that is the hazards, vulnerability and exposure. In the step 3 of the phase 1, you identify your risk like urban ecosystem stress, UHI, air quality, urban flood, depletion of groundwater. So you can do these many risk study using the Geosm-Natec framework. So for each one, the hazard is land use typology, LST-80, PM data, runoff depth, groundwater recharge. So these are the information you need. And the vulnerability information, normalized NDVI, NDWI, NDBI. And for this water related one, you need NDVI, NDWI, NDBI, as well as urban hydrology, stream order, stream network, stream density and the slope. For the exposure for this first three, like urban ecosystem stress, UHI and air quality, population density is important. And for the water related stresses, you need land use typology as well as the population density. So once this data set is being collected, then you come to the second phase where you prepare the geospatial layers. In this, the first step is mapping of each geospatial layer on the GIS platform: NDVI, NDBI, NDWI, and LST. We will talk about them. I know some of you are quite acquainted with them, but let us also have a brief discussion. Normalized difference vegetation index. The NDVI is the primary metric for ecological readiness. It exploits the red edge characteristic of healthy vegetation, which absorbs visible red light for photosynthesis and reflects near infrared light to prevent overheating. So the NDVI is defined by the difference between the NIR, near infrared, and the red, and which is divided by NIR plus red. And the range is -1 to +1, the value you get. If the value is more than 0.6, which indicates the dense healthy vegetation, forest or parks, if the value ranges between 0.2 to 0.4, that indicates sparse vegetation, shrubs, lawns. In between 0.4 to 0.6, you have to take a decision. Values which are less than 0.1 indicate barren rock, sand and snow. Urban application in the Geosm-Natec, NDVI is used to monitor the loss of green cover over time. Like in Jaipur, we have seen 18% decline, and to validate the cooling potential of existing green spaces. Normalized difference built up index, NDBI, that effectively delineates the grey infrastructure. Built up areas typically have higher reflectance in the short wave infrared region than in the near infrared region. So NDBI is defined by the difference between short wave and the near infrared divided by the short wave and near infrared. And the value again ranges between -1 to +1. Positive values indicate built up areas, buildings, roads, etc. And negative values represent non built up areas like water or vegetation. Urban application of this NDVI. NDVI maps are crucial for quantifying imperviousness. High NDVI values are directly correlated with increased surface runoff like flood risk or higher LST for heat risk. So that's the way we interpret NDVI. And the next one is the NDWI, where W stands for water, and this is used to highlight open water features in a satellite image, allowing a water body to stand out against the soil and vegetation. So it is green minus near infra divided by green plus near infra. And the range is again -1 to +1 for the values. If the values are closer to +1, that indicate more water like open water bodies or saturated soils, and values closer to -1 that indicate less water or dry land like built up areas or bare land. The urban application of NDWI is essential for mapping shrinking wetlands, encroached canals like Chaktai Khal in Bangladesh Chattogram. We had done a study at one time, and potential zones for water retention. Then we come to the land surface temperature LST, which is a key indicator of the urban energy balance. It is derived from the thermal bands of satellites such as Landsat or MODIS. The process involves conversion to spectral radiance, converting the digital number DN to radians. Brightness temperature, converting radiance to effective temperature using the Planck constants. And emissivity correction, adjusting for the material properties of the surface, like concrete emits differently than the grass. LST, and you can find here a formula to calculate that LST, that is brightness temperature divided by 1 plus lambda. Lambda is representing here the wavelength of that multiplied by the brightness divided by the Planck constant, and it's having a logarithmic function of epsilon, that is the emissivity. So using this formula you can calculate the LST. And now we will come for the next step of the phase 2, that is preparation of geospatial layers. In this step, we do the overlaying, the grid, and extracting data from each layer. Scale of the study like microscale, mesoscale, macroscale, it matters. Spatial resolution of the satellite data used for the study, and 1 by 1 kilometer grid size assumed to be the best fit size for the data of 12 to 100 meter spatial resolution. Mean of each layer has been quantified grid-wise in respective units and exported in CSV format for further analysis. And this is a very lengthy but very important step. That's the step 6, analysis of grid-wise data as per predetermined conditional approach. So higher the value of NDVI, lower the potential of risk, ascending order. Higher the value of NDBI, higher the potential of risk. So it's a descending one. Why? Because we are having lot more built surfaces. Higher the value of NDWI, lower the potential risk because we have lot of open water bodies to absorb that additional water. So it's a ascending order. High the value of LST, higher the potential of risk. So it's a descending order. Higher the value of the aerosol distribution, higher the potential of risk, ascending order. Likewise, for the runoff retention, higher the potential of risk, ascending order. Groundwater recharge, lower the potential of risk, descending order. If the value of slope is high, then potential risk is low. The value of stream density is high, then the potential risk is high. Likewise, the last one is the stream network value, and if that value is high, then potential of risk is also high, then it is in ascending order. So that's the way this predetermined conditional approach is getting satisfied. And step 7 is identification of risk zone categories and hotspots. So now the entire grid will be divided into 3 risk categories, each including an equal number of grids: high risk, medium risk, and the low risk. Hotspot grids will be identified by selecting grids that either appear in all layers or are present in the maximum number of layers under high risk categories. The hotspots grid number has been identified and respectively mapped on GIS. We will also discuss the same process with an example later on. And next step is the validation. Many a times we also have done this validation on ground truthing. That is also very important to make sure that whatever you are getting out of this system, whether you can explain those phenomena. Step 9, identification and categorization of the blue-green infrastructure potential zones, and then the outcomes in the phase 3 is the intervention zone. Intervention zone: proximity to the highly affected zones, presence of public buildings or open spaces, because if it is a public building or open space, then it is easy to think about some intervention through the nature-based solution. Locations adjacent to critical infrastructure or residential clusters are prioritized to maximize the impact. So there are always reasons that where to intervene so that you can optimize the benefit of it. Areas showing consistent ecological decline, that can be a potential area. Regions showing declining groundwater tables but possessing suitable geological condition for artificial recharge structures, that can be a very important intervention potential point for the groundwater recharge. Sites approved by residents, urban authorities, and other stakeholders are favored so that you can ensure long term success and maintenance. That is very important. Examples of suitable intervention zones are urban parks and green spaces, abandoned or vacant plots, rooftops and building facades, ponds, lakes, and canals, etc. Geosm-Natec framework potential solution. Conceptual methodology. Geosm this actually offers solution for the preservation of the areas with pre-existing healthy ecosystem. It advocates about restoration of areas that are showing signs of degradation. And this suggests, Geosm-Natec framework suggests revival of areas that are under threat. And you can see the things together for the urban flood. So you identify the study area or research problems, so your study interest area is here. You go for lit review and the case study analysis. You collect the visual and physical survey data. Then you go for the earth observation data and analyze it from the city to local level, as we discussed in phase 2. Major focus is the urban risk, and we see that overlaying GIS maps using the Geosm-Natec framework and identifying potential zones for implementation of nature-based solutions, which just now we discussed. Then you check the efficacy of that NBS for identified urban risks. As it is a framework, it actually allows us and supports us to use many such software. So you can use a tool here, simulation tool, to look at the efficacy. And from that, you can actually have some good inferences on the urban risk resilience side, nature-based strategy, which one you are picking up, that also you can identify. And in addition to that, you are not only working as an ecologist or a governing person or a risk manager, but you can also go for the urban design strategies: place making, recreation, well-being, sustainability, economic boost, and the imageability. You can play around all these points. So that's the strength of the Geosm-Natec framework. So it works with the advanced tools and technologies which are enabling to bring out the complexity of the city system, and you are not only being able to identify the problem areas, the hotspots for any risk, like it can be UHI, it can be air pollution, it can be groundwater depletion, it can be the urban ecosystem stress, that loss of biodiversity or ecology, and also the flooding. So you can do that, but also not only you can identify the hotspot for the stresses, you can also identify the potential areas. You can simulate them to see the efficacy of your strategies once you select the strategies. And then you can come back through the community participation for implementation, and you can check how best it is really delivering the ecosystem services. So this Geosm-Natec framework for urban flood is the situation of water logging in an urban area for a longer period of time. That's the definition of this urban flood. How NDMA defines it, urban flooding is significantly different from rural flooding, as urbanization leads to developed catchments, which increases the flood peaks from 1.8 to 8 times and flood volumes by up to 6 times. Consequently, flooding occurs very quickly due to faster flow times in a matter of minutes. The notable of the flood events in India, urban flood events in India, are in Hyderabad in 2000, Ahmedabad 2001, Delhi 2002 and 3, Chennai 2004, Mumbai 2005, Surat 2006, Kolkata 2007, Jamshedpur 2008, Delhi 2009. You can see each and every year, even there was no gap, and we have not mentioned so many other cities like Gurugram. It is facing problem. We are also now getting the reports of those cities which has never faced problems, from northeast to west India, western India. Everywhere we can find the examples, whether it is Shilchar or whether it is Barmer. Remote sensing and GIS, it help in mapping topographical and geographical feature of urban settlements. That's the strength of the Geosm-Natec framework. It maps both natural and man-made influencing factors responsible for urban flood. Remote sensing helps in mapping meteorological parameters such as rainfall, temperature, RH, risk zone considering urban parameters or features responsible for urban flood, urban natural and man-made catchment delineation, streams network delineation, rate of urbanization delineation and change in LC, runoff or discharge quantification, probable site of inundation zone delineation. So remote sensing can help us in mapping so many parameters. You can see here local drainage area you are having, which is part of an urban subcatchment. And this urban subcatchment is part of city area, and the city area is actually sitting within the river basin region. So that's the way we have to understand that when there is a urban flooding, we need to understand this hydrological modeling a bit. Natural catchment, large catchment size, river, stream, natural LULC. Urban catchment is a modified one. It may be small catchment size, but it is also influenced by the natural as well as the urban. Major and minor drains are there, altered LULC is there. And when you work for urban flood, these are the type of layers you create for hazard map based on the indicators: flood volume, run-up depth, precipitation, low, medium, high for the hazard. And for the exposure map, the indicators are NDBI, population density, critical infrastructure, geotagging, the infrastructure is important, land use, land cover, urban hydrology like basin catchment, stream network, stream order, and land use typology. In the vulnerability map, we use the NDVI, NDWI, soil hydrology, urban hydrology, elevation, stream order, stream density, relief, flow direction, etc. And the last and most important part of the vulnerability map is the socio-economic one, that status, income group, age group, at what level. So today what we have discussed? We have discussed the summary of the modules 6 and 7, which we have done several weeks back, and we have discussed about the geospatial mapping of natural ecosystems, Geosm-Natec framework, its details, architecture, methodology, potential solutions, and we brought the example of urban flood to understand this framework better. With this, these are the reference list. Thank you.